Guys, if you remember when we started this course, we talked about the electric force that acts on a charged particle in an electric field. And we said that that force equal to Q times E. If you have a charged particle, and if you put that charged particle inside an electric field, there will be an electric force on it. That force will equal to Q times E. Now we're going to talk about having a charged particle moving with a velocity V inside a magnetic field. And we'll calculate the magnetic force acting on that particle. So this is mainly chapter 29. As we started chapter 23 by studying the electrical force, now we're going to study the magnetic force. So we're going to have an introduction about the types of magnets and the magnetic phenomena and magnetic field lines. We'll talk about monopoles and current. We'll talk about some application of magnetic field and magnetic forces. This is the continuation of Lorentz force. Lorentz force, if you look back at that slide, this is Lorentz force. This is the force from the electric field. If you have a charged particle in electric field and the magnetic field, if the two of them are present, we call that Lorentz force, or if one of them is present actually. Then we'll talk about the motion of a charged particle in a magnetic field. We'll describe that motion by equation. And Lena, when we say that we'll describe that motion by equation, we mean we'll describe that the path of that particle during motion inside a magnetic field. So we're going to go back to the kinematic equation that we have used in Physics 111. In order to describe a motion of an object, you need displacement, velocity, and acceleration of that object. Okay? So magnetism, that's people in the old era, 2,500 years ago, they discovered that some stones have this ability of attracting metals. And those stones were found in Greece, and they will actually they were found in a district called Magnesia in northern Greece. That's why we call them magnets. People found that if they hang a magnet in the air and make it free to move, it aligns itself in such a way it points to the north and the south pole of the earth. And this told us that the earth itself has a magnetic field, and that magnet aligns itself inside that magnetic field. So if we look at any magnet, and we'll have actually tomorrow, I'll show you a real demonstration for the magnetic field. Any magnet will have two poles, one that will point to the north pole of Earth, and the other one will point to the south pole of the Earth. That's why we call them north and south. Between them, those north and south pole, there is a magnetic field, and this is a typical magnetic field from a power magnet. This is a power magnet. This is a typical magnetic field. The magnetic field goes out from the north and goes into the south. So this is a typical magnetic field. And actually, it's similar to something that we have studied before. If you remember, electrical dipole, positive charge and negative charge. Positive charge goes electric field goes out from the positive charge, electric field goes out from the positive charge, and goes into the negative charge. It's similar to here. The magnetic field goes out from the north and goes into the south. So actually those are similar, except one simple difference between them. If we go and take that positive charge alone, will it have a dipole, or will it be a monopole? Monopole means it's only one charge. It has only electric field goes out from it. So if you take that positive charge alone, you can get what we call it a monopole, only one charge that has a field around it. But if you take this magnet and break it into half, then you break it into two halves. Then you get north, south, north, south. You take this and break it into another two halves. You get north, south, north, south. You keep on breaking this magnet into small pieces. Each time you break it, even if you break it into very, very tiny magnets, you get a dipole, north and south all the time. So in magnetism, there is nothing called monopole. You cannot have a north pole by itself, or you cannot have a south pole by itself. There is always a dipole. Okay, this is the difference between electricity and magnetism. Guys? Oh, it's dipole because it has two poles. Dipoles. So it has two poles. That's why we call it a dipole. And this we call the. Yeah. Inside the magnet itself, the field goes from the south. It has to close the circuit. It goes from the south to the north. Inside the magnet itself. How come? Inside the magnet and south to north. Yeah. And in electric field, you can have a monopole. In magnetic field, this is the most important part. You cannot have, there is nothing called a monopole. And guys, if one of you come up of a way to get a magnetic monopole, he will get Nobel Prize. So, if you have a magnetic field, if you have a magnet and you bring a piece of metal close to it, of iron close to it, what happens? If you have a magnet, you bring a piece of iron close to it, what happens? It gets attracted to it. And if it moves, then it means that there is a force acting on that piece of metal. And that force, we call it a magnetic force. Now we are very interested in calculating that magnetic force. Now we're going to start calculating the magnetic force on charged particle. So if you have a charged particle Q, electron or a positive charge inside a magnetic field close to the magnet, what happens to that charge? So simply there is the application of Lorentz law. By observation, we have observed the following. If you have a charge inside the magnetic field, if that charge is at rest, if it's not moving, nothing happens to it. It does not get attracted to a magnet to the magnet. It does not move at all by a magnet. If you have a charge by itself, and if that charge is at rest, nothing happens to it. There is no magnetic field on it. But if you have the charge moves inside the magnetic field, there will be a magnetic force on it. And the direction of that magnetic force is always perpendicular. All of this is by observation, guys. Or what I'm saying now, we have observed that in the lab. If you have a charge that moves in a specific direction, there will be a magnetic force perpendicular to the direction of the motion and the direction of the magnetic field. So let's assume now that I have a magnetic field goes from that side of the room to that side of the room. This is the direction of the magnetic field. Okay? And this is the direction of the motion of the object. Moves in that direction. What will be the direction of the magnetic force? It's going to be perpendicular on both of those. It's perpendicular to the magnetic field, and it's perpendicular to the direction of the motion. The only direction that's perpendicular onto those two directions is either up or down. So is it up or down? Is it up or down? It's according to the right-hand rule. The right-hand rule. This is the right-hand rule. This is what I say. This is the direction. Those lines represent to us the direction of the magnetic field. So you always point those fingers, 4 fingers, into the direction of the magnetic field. Wait, I'll do it in a different way. Okay? The reason that I'm doing it in a different way, that you till now, though we have studied that so many times before, you do not remember it. So I'm going to give it to you in a little bit different way. You may be able to remember it afterwards. So those lines represent to us a field lines. Field lines. Makes sense. This will represent to us the direction of the motion. So I'm going to follow my example. I said this is the direction of the field lines, right? And that was the direction of the motion, so I have to flip my hand like this. Now the particle will have a force in that direction, as if you move it with your forehand in that direction. So this will be the direction of the force. I'll say it again. Those four fingers, if you look at them, they represent the field lines. They look like field lines. So this is the direction of the field. The thumb will be always the direction of the motion. So in the example that I showed you a minute ago, I said that this is the direction of the field. This is the field line, the four fingers. And the thumb should point to the direction of the motion. And I said this will be the direction of the motion. So I have to flip my hand. So this will be the direction of the force. Okay, guys? So in this, we call that the right hand rule. There is other way to do it, that way. That's okay.
What's the difference between direction of the force and direction of the motion?
Okay. Initially, the object, that's a very good question here. Initially, the object enters the magnetic field in that direction. In that direction. After some time, there will be a force attracting it down. This is the magnetic force applying it. Then it will return down. So change direction. And actually, as change direction, if the direction changes, the direction of the force will change accordingly as well. So it keeps in direction or changes the direction. As a matter of fact, if you have a particle, positive particle, enters that room, and this is the direction of the magnetic field, this is what happens. It will rotate in a circle. And the reason that it will rotate in a circle that once it enters the room, it will feel the magnetic field that it will push it a little bit down. So this will be the new direction of the motion. And the direction of the force, it's going to be inward in that direction. Now, look at my hand. It's in that direction now. So, that direction. And so the particle will point in that direction. Now the motion is in that direction. And the force will keep changing. The force will keep changing the direction of the motion, and eventually you will have a particle that moves in a circle. And we can calculate the radius of that circle later on. And by common sense, it will depend on the velocity, initial velocity of the object. It will depend on the magnetic field, and we'll calculate that in a few minutes. So, good observation. Okay, Tariq, to be honest with you, it always bothers me to do it that way. I like it that way. So, but anyway, it doesn't matter which is which. It doesn't matter which is which. So you tell me, this is the field, this is the motion, that's the force, right? Right? Okay, so this is the field. Oh, this is, okay. Field, motion, force. That way is much, much easier. The force is as if you're slapping someone. Okay? Field, motion, force. Assuming that the charge is positive. But if the charge is negative, all what you do, good night. Yeah. All what you do is you assume that it is positive and reverse the direction afterwards. Reverse the direction of the force afterwards. That's all. Okay? I cannot do this. It's impolite to do it. So you can hit that way. That way it's too... Okay, so guys, look at those three diagrams. In here, the crosses, Abdullah, Attabi. Crosses means the magnetic field is into the page. That cross means this is the tail of an arrow. And usually that's how we draw the arrow. So if you look at the tail, it will look like if it's a cross. If you look from here, it will look as a point. So if I do this, this means that the magnetic field is into the page. And if you do this, that means that the magnetic field B is the symbol for the magnetic field, is out of the page. So here we have the magnetic field. The magnetic field is into the page. This is the direction of the motion. V is the direction of the motion. What will be the direction of the force? So again, field, motion, force. And here, this is the direction of the field. Field, motion is up, then the force is into the screen. How about here? The velocity and the magnetic field are parallel. And the condition is the force has to be perpendicular to the two of them. Actually, if they have a parallel, if the velocity is parallel to the magnetic field, the force in there is going to be zero. And this will give us the Lorentz law for the magnetic force acting on an object. Again, Lorentz law says that it's the force, the magnetic force, equal to the charge, the magnitude of the charge, times the velocity, cross the magnetic field. You have to do the cross product between V and B. Do you remember what is the cross product? Do you know how to do the cross product? A cross P. Two vectors, A cross P, will give us a C, which is also a vector, and C will equal to the magnitude of A times the magnitude of B times cosine the angle between them. Are you sure? Yeah, thank you so much. Yes. Dot give you cosine, this give you sine. Thank you. This is in one dimension. If you have A in one dimension and B, B is also in one dimension, then simply C is another vector, and it's going to be A, the magnitude of A times the magnitude of B times sine the angle between them. But if you have vector A is in 3 dimensions, and vector B is also in 3 dimensions, how can you find the magnitude of vector C and the direction? So you have to do this. Determines, yes. Or this is the vector A in 3 dimensions, cross vector B, that's vector B. Now, how to do the cross product? Guys, if in physics 111, we came up with that smiley face. I cross J give you K. So if you multiply a vector along the I direction, cross a vector along the J direction, you get a vector along the K direction. J cross K, you get I. How about K cross I? You get J. And if you reverse the direction, if you say J cross I minus K. If you say K cross J, it's minus I. And if you say I cross K, it's minus J. How about I cross I? 0. J cross J, 0. And K cross K, it gives you 0. So if we apply this simple smiley face in here, you get A cross B, 0. Plus A cross I cross J, K, something K, and this is going to be the magnitude of A times the magnitude of B. No, I cross J, you get K. I cross J. I cross J, you get K. Okay? For the determines, yes, you can do it. No. Trust me, no. Because not all of the people actually know how to do it with the determinants, then I'm not going to do it that way. But trust me, do it at home and compare the two of them, you get exactly the same results.
So doctor, I consider a minus zero.
And Ala, if you finish the whole process, you will find the negative that you're actually looking for. It will come from J cross I.
ايوه يا دكتور لما تعمل لو عملتها بالديترمنت لازم احط الجي بالمنش. لو عملتها اللي هي بالطريقه بتاعت اللعبه.
The most important is you're looking at the step by step. Look at the big picture. After you finish, we get the same results. You do it with determinants, I do it with that method, you get exactly the same results. So guys, we say AX times BYJ, you get AX BX times along the K direction, and if you continue doing this, you will get A cross B in 3 dimensions. So it's not a hard thing.
The only explanation for the hand rule is observation or the explanation?
Actually, it's observation. It came by the beginning by the observation. They did the experiment so many times, and each time they find out. They find out that actually the rule applies that way. Okay. So saying that, giving you information about how to find the direction of the magnetic force. So Omar, then Heba will tell us the solution for those 2 problems. Bakri? We have 3 points arranged in a uniform magnetic field. You see those crosses, this is a uniform magnetic field, and we have 3 points in them, A, B, and C. The magnetic field points into the screen. You have a positive charge, is located at point A, and it's stationary, it's not moving. The direction of the magnetic force on the particle is. Why is it 0? Because there's no motion. So good. Now the positive charge moves from point A to point B. The charge will move from A to B. What will be the direction of the force? This is the direction of the motion from A to B. It's going up. Yeah. Not using the right hand. So it's going to be, this is the direction of the magnetic field. It's into the screen. This is the direction of the motion. This will be the direction of the force. This will be the left. So let's look at the solution. I almost said 0. There's no direction. Computer. Right? And it's correct. Okay, now we'll complicate that a little bit more, and Nina. Now the positive charge will move from A to C. What will be the direction of the force? Nina. You have to try. No. In my dictionary, there is nothing called مش عارف. I have no idea what does that mean. I never take that. Just try. What are we supposed to do? No. What are we supposed to do? How can we find the direction of the force? So what did we say all day today? Okay. Again, we said that if you need to find the direction of the magnetic force, you have to find the direction of the magnetic field. So what is the direction of the magnetic field in that problem? It's into the screen. The crosses, those crosses that you see them, this means that this is the direction of the magnetic field. It's into the screen. And those fingers, they should point into the direction of the magnetic field. Okay? Okay? Okay. Now, what is the direction of the motion? It moves from A to C. This is the direction of the motion. Now, my fingers point into the direction of the magnetic field. The thumb points into the direction of the motion. This should be the direction of the force. So the direction of the force is up and left. Okay? Okay. So I'll give you a minute to think about that. We have two protons. Protons mean they are positively charged. They move at speed v, as shown in on the figure, in a region where the magnetic field is pointing into the negative z direction. The magnetic field is into the stream, and negative v direction is into the stream. What is the relation between the magnitude of the force on the two protons? Magnitude. Yes. Only magnitude. Oh, it's Lorentz law, which states that force, magnetic force, equal to Q V cross speed. So if we're talking about magnitude of the magnetic force, then it's Q V times V.
F1 equal F2.
F1 is more than F2. Abdullah is saying F1 is going to be more than F2.
Should we consider the answer equal? Equal because the magnitude
At that stage, they will be equal. Yeah, I'm asking all about the magnitude. I'm not asking about the magnitude.
F1 is greater than
So,
there's no
actually, it's saying F1 equals F2. Wait, we'll open the discussion later. Let's just get the answers, then we'll open the rest of the discussion. Asad is saying F1 equals F2, and Abdullah is saying actually F1 is going to be more than F2, right? That's what you said, yeah? Okay. So the answer is either B or C. Does anyone think that the answer is A? Asad? So what do you think the answer is?
Because according to the equation, the magnitude of the equation, like there's no crossroad and there's no direction. You're not asking for the direction.
I'm not asking for the direction, but I'm not asking for the direction, I'm asking for the magnitude.
And the magnitude is that's it. Same Q, same V, same B. And it's 3 close V. Not the same V.
Same V, yes.
Oh, we have the
Can I ask you something? Let's assume that that velocity has two components. One along x and one along y. Which component will contribute to the magnetic force?
The one on the X. The one on the X.
To be? Let's look at that. How about okay?
الانجل ده فين؟ دي مع
This is the angle, guys. Again, this is the angle of the velocity, right? This is the angle of the velocity. This is the angle of this is the direction of the magnetic field. What's the angle between them?
Right.
So that's part one. Part two. What is F2x, the x component of the force on the second proton? Is it positive, is it negative, or is it zero? The second, the x component of the force on the second object. So why is it positive? What positive? What does positive mean? Direction. So positive or negative means only direction. So actually in this problem here is asking us mainly about the direction of the x component of the force on the second object. So what will be What will be the direction of the force? This, that.
What's the y negative?
So this is the direction. This is the direction of the force. And it will have two components. One along negative x and one along positive y. So let's see if this is correct. Part 2. And you have the explanation. Okay guys, that's good. Part 3. Inside the magnetic field, what happens to the speed of the object, of the process? What happens to the speed of the process? What is the meaning of speed? Only the magnitude of the velocity. What happens, you remember what the Umar asked? What did Umar ask 15 minutes ago? He said, what happens to the direction of that object after it goes inside the magnetic field? And I explained that. I said at the beginning, if the object goes in that direction and the magnetic field is in that direction, the magnetic force is going to be pointing down. So it will point down at the beginning. Then this will keep change. The direction of the magnetic force will keep changing because the direction of the motion keeps them changing. Only the direction of the motion keeps them changing. The speed stays the same. The velocity changes. And this is going to be a uniform circular motion that we have studied in Physics 111. And one of the definition of the uniform circular motion, speed stays the same, the velocity changes because the direction keeps on changing. So it stays the same. Okay, now let's look at the path of that object inside a magnetic field. Back to what Omar said at the beginning. So we have an object, a charged particle, positively charged particles. It's going to enter from a region that has no magnetic field into a region that has a magnetic field. And let's look at what's going to happen at the beginning. It goes in that direction, and there will be a force acting on it along that direction, along to the left. So it will bend the motion a little bit. The motion will bend in that direction. So at that point, as the motion is bending, the direction of the force is going to be pointing in that direction. If you follow the right hand rule again, here, same thing. And at that point, if this is the direction of the motion, and if this is the direction of the motion, and this is the direction of the magnetic field, this will be the direction of the force. At that point, this is the direction of the force. At that point, this is the direction of the force. Guys, look at the direction of the force all the time. It always points into one point. It's along the center. So this, if you have an object that goes inside the magnetic field, it will move as the velocity. If the speed does not change. If you do not change the speed, and if you do not change the magnetic field, that's why I said constant magnetic field, the path is going to be circular. It will move in a circle. The force always points into the center. Now what we are interested in to measure that radius, actually that diameter. Can we measure that radius? Any idea how to do it? Kinematics, how about Newton's second law? Sorry, saying, well, if you talk about Newton's second law, then I will look at that object. I will apply Newton's second law. So if I draw the free body diagram for that object, that's the object. We'll draw the free body diagram on it. So the free body diagram at the beginning. This is the force. This is only magnetic force. Do we have any other forces acting on it? No, actually, you remember at the beginning when we compared electric field, electric forces to gravitational forces, it was very small, and it's the same here. So we're going to assume gravitational force. But we're going to ignore gravitational force. Totally ignore them. So we have only magnetic force. So we apply Newton's second law that states that the net force, or sum of all forces acting on the object, will equal to the mass and the acceleration of that object. the force acting in the object is that it's QVB will equal to the mass times the acceleration.
How is QVB as a magnetic field?
No, as in because the direction, the angle between V and B is 90 degrees, sine 90 is 1. Okay? This is what are the forces acting on the object? Velocity. QV cross B, but the cross product A will plus 1, that's why I said QVB. QV cross B. But because they are perpendicular to each other, V and B, then I will, the cross product will give us 1. Equal mass times acceleration. What kind of motion do we have? Uniform circular motion, in which the acceleration equal to the velocity squared divided by the radius. Right? Chapter 4, Physics 111. Now, guys, when you solve for R, V will go with the square. R will equal to mv over qv. This equation tells us, if you tell me what kind of object, what kind of particles do we have, I will know what the mass and the charge of the particle. If you tell me the velocity and the magnetic field, I will be able to calculate the radius of that motion.
The mass is that
The mass of the proton and Q is the charge of one proton. Then if you specify in the experiment what is the velocity of V, what is the magnitude of V and the magnitude of the magnetic field that's N, you will be able to calculate it.
هو ليه المagnetic force دايما pointing to the
That's by applying Lorentz at that point.
اكيد يفهم يعني الفرق مثلا بيبقى فيه يعني اكيد يفهم معايا ان هم دايما عشان كده ولا دايما ولا عشان دايركشن
Because of the direction of magnetic force. The direction, you calculate you find the direction, and you wherever the particle is at, or wherever the location of the particle, the direction of the force will always point into the center. Okay?
the force the first slide or force equal to QE, which is equal to QG plus, huh?
Yes, plus. So I said at the very first slide, I'll go back. At the very first slide here, we said, if you have an object, a charged particle, Q, and if you put that charged particle in a magnetic field, in an electric field, and magnetic field, then this is the force acting in the object. But if you put it only inside a magnetic field, then the force equal Q, V plus V. If you put it only inside electric field, then the force equal Q times V. And that's a proof.
Oh, and a magnetic force acts as a centrifugal force, that's why we have a circle?
And actually this simple experiment very, very useful for us because it gave us an idea on how to calculate the charge to a mass or any particle. If you have a particle and you would like to know what is the ratio of mass, its charge, simply specify velocity for that particle. Put it inside a specific well-known magnetic field, measure the radius, you can calculate that ratio. And this is very important for chemists or people who work on the pharmaceutical industry. They can get to know the type of material they use if they keep on measuring Q over M, calculating Q over M, then they can get information about the material we have. So they put a material inside the spectrometer that we'll see in a minute, and all what they do is they keep on changing V and V and measuring R, and from that they get the ratio of Q over M, and that tells us tells them a lot of information about the material they are using. So anyway, guys, that was one of the problems in physics exams. It says that you have a charge that 25 million coulombs that enters with a velocity equal to 75 meters per second at chamber number 1, as you see. Then it bends and goes inside the chamber number 2, then it bends and goes out of the chamber number 2, as you see the path of that charge. Now, I'm asking you what will be the direction of the magnetic field in chamber number 1? Just a door for that chamber. So what you have is a room, that room number 1, that's room number 1. The box is going from in, from that room, it is bent and goes into the second room. And from the direction of bending, I would like to know what is the direction of the magnetic field in room number 1. Again, right hand rule, not left hand rule, right hand rule. Obviously, at the beginning, what is the direction of the force? Because it's actually going to bend that way. So at the beginning, this is the direction of the force. What is the direction of the motion? Up. Up. So what should be the direction of the magnetic field? That's easy. In the exam you will look crazy or if you're doing it, that's fine. We all the same. Okay, about the direction of the magnetic field in chamber number 2. What is the direction of the force? At the beginning, at the very beginning. Up, thank you. It's up. So this is the direction of the force, up. What is the direction of the motion? To the right. So what will be the direction of the magnetic field? Again, show it again. Which one of them? How about the substance? First one, they go to the second one. So how I think about it? Well, I look at the motion, and at the beginning, obviously, the object has been pushed to the right. So this is the direction of the force. If you push something to the right, it will move in that direction. So this is the direction of the force. So this is the direction of the force. What is the direction of the motion? The object goes up. From here, from there, up. So this is the direction of the force, this is the direction of the motion, this line, field line, is the direction of the magnetic field. Alright? Chamber number 1. How about you do chamber number 2? What is the direction of the force? Up. It doesn't matter, up. Okay. Then, what is the direction of the motion? To the right. To the right. So then the force is up, motion is right. What is the direction of the magnetic field? What way? Okay. Do it again. Convexus. But now the motion is down. The motion, the direction of the motion, your thumb is pointing down, not up. Yeah, this is the... No, but yeah, but you know, I say, would you like to teach? Would you like to stop talking? Please, he can ask me, you're not the teacher. So, that's it. In order to find the direction of the force, or the direction of the magnetic field, I have to know the direction of the other two axes, which is the motion, or the force, or the magnetic field. You have three things: motion, magnetic field, and force. So in this case, you say, well, do your hand again? Yeah. That's correct. This is the direction of the motion. It's the right, my right. Okay? But look at your finger now. This is the direction of the motion. It's pointing down. This the particle is not moving down. It's moving up. So this should be down. So, guys, into the page in chamber number 1, out of the page, that is correct. Into the page, that is also what was correct. Now,
I shall examine how I will explain it.
that's very easy. Direction of the motion is up. The direction of the force is to the right. That means that the direction of the magnetic field should be perpendicular to both of them. That's into the page. Now, more important. Which room has which room has stronger magnetic field? One. So, well, the guys looked at the equation and they said actually you increase the magnetic field, the radius is smaller or chamber number 1, which is not correct. Okay? More important, you have two objects, two protons. One is moves with the velocity v, and the other one moves with the velocity v1, which is double v, 2v, v and 2v. And we need to compare the work done by the two. We need to compare between the work done by the magnetic field on the two protons. Work done. Everything will, I should calculate the force first, then the force dot displacement, that should give us the work. That's the perfect answer. Can we do it? So Heber gave us actually how to do it. Heber said we should calculate the magnetic force first, then find the work, and the work is going to be the force dot the displacement. And she says that actually, but the force and the displacement are perpendicular to each other. And there's no work, because the dot product in that case will give us 0. The work done equals to the force times the displacement, distance, times cosine the angle between them. So the angle between the force and the displacement is 90. There's no work. So in that no cases, the work done is 0. It's equal, right? Doesn't matter. So it's 0 actually in the two cases, and that's why you get exactly 1 equal to that. Okay, let's do it one more time. In case number 1, the work done is 0. Because the force and the direction of the motion, which is the displacement, are always perpendicular to each other. And the work done, as we know, work done is equal to force dot displacement, which is equal to force magnitude of the force times the magnitude of the displacement times cosine the angle between the two of them. What's cosine mean? 0. So in the two cases you get 0 work. That's why W, work in number 1, case number 1, equals to work in case number 2.
How come theta is 90?
It's okay. What's theta?
Theta? The angle between the force and the magnetic field?
Is it? Is it? Why? Why do you think so? Why do you think it's the angle between the force and the magnetic field?
And if they're perpendicular, but cosine 90 is 0.
Oh. How did he get to know the angle theta is the angle between the force and the magnetic field. Why not the force and the displacement? Okay, guys, work done. Work done. Definition of force, regardless of the type of the force. If it's electric force, magnetic force, you push something, you pull with a rope, regardless of the type of the force, equals to the force dot the displacement, which means this equal to the magnitude of the force times the magnitude of the displacement times cosine the angle between them, and them refers to force and displacement, not the magnetic. So now, look at the force and look at the displacement. Force and displacement, force and direction are always perpendicular. So go back. Force and direction of the motion are always perpendicular. Force and direction of the motion are always perpendicular. So the force and displacement, the angle between them always 90 degrees, and there is no work done by the magnetic force. There will be work done by the magnetic force. And think about it. If there is the work done, that will change the kinetic energy. If the kinetic energy change, speed will change. And that does not happen. Okay, guys, so I'm going to start Hall effect tomorrow. Hall effect is the application of what we have studied before today. We are going to start that tomorrow. Remember, there's an assignment due tomorrow.